So connecting the idea from basically non-parametric regression to the normal means model. So if you have a non-parametric regression model like this, the observations are yi's, the true function is fs star. Xi's can be in a general space, usually a subset of Rd for us. And you assume that fs star is in some function class, subset R to the X. This is my notation for the class of all functions, real valued functions on X. And so a natural estimator in this setting is this projection estimator. So you minimize the least squares error between yi and f of xi as f varies in the function class. So whether you can solve something like this for a general function class is a good practical question, but as I mentioned, for now, let's assume that we can solve this. Or even if we can't solve it, we can try to approximate it or basically analyze it, even if we can't find the function. The question is, what can we say about the properties of this estimator? This turns out to be also the maximum likelihood estimator. If sigma is known, if you try to maximize the likelihood, that's what you get under the Gaussian setting. So this is also the MLE. Also the MLE under Gaussian, the Gaussian assumption, and the noise. So known with known variance. So we can map this to a normal means model, as I believe we discussed last time. So if I divide both sides of the first equation by 1 over, or by root n, so this gives me f of xi divided by root n plus sigma over root n wi. We can call this theta star I, call this yi tilde, and call this this sigma tilde. So we have a model yi theta star I and then sigma tilde here. If you put together everything in a vector, so you get y tilde is theta star plus sigma tilde w. That's another way of writing it. So everything is now in Rn. And this theta star is this map applied to fs star. So this map is a sort of sampling operator. So it takes f and maps it to a vector in Rn with this scaling, which hopefully becomes clear later on why we do this. And the function class, as f varies in the function class, phi of f varies in a subset of Rn. So that gives us sort of the theta. If you recall, there was this subset theta, capital theta, in which we assumed the true parameter lies, and in fact, in this case, because fs star belongs to, so fs star belongs to f, this implies that theta star belongs to this capital theta. Okay, so with this model, so if I also map this f hat to theta hat by this phi, in other words, theta hat I is f hat xi divided by root n, then it's not hard to see that how is it not hard to see? So if I have f hat is arc, then 1 over n summation yi minus f xi, right? I can write this as basically argmin f in f summation. I'm going to move 1 over n inside the square, basically. So I get y tilde minus fxi divided by root n squared, right? And there's a yeah, 1 over n right there. So this is also equal to, here. This is also equal to argmin f in f. Now I can write it as y tilde minus this map applied to f gives me a vector. So now everything is in R2. And as f varies in f, so I can think of the, if I look at basically phi of f hat, right? Phi of f hat would be basically argmin phi of f as f varies in f, y tilde minus phi of f. This is, you can say that this is theta hat is argmin theta such that theta belongs to theta, y tilde minus theta squared. So if you think of only the samples of f hat, the samples of f hat follow this projection, sort of basic projection. This is the projection estimator in the normal means model. Okay, so projection estimator. Okay, so basically you have this and you have y tilde I is theta star I plus sigma tilde wi, I from 1 to n. Wi's are IID standard normal. So this is exactly the setting that we studied. The only difference is that this theta is coming from a function class via this map. Right. So the complexity is sort of induced by the complexity of the function class. Okay. So if you recall, any questions so far? So if you recall, the results that we had sort of allowed you to connect the behavior of this estimator to the solutions of this critical equation. So this critical inequality, basically. We looked at the smallest delta that satisfies this. And then we saw that, for example, the normalized error basically would give us, or is determined by this delta n squared plus sigma squared over n, and this usually dominates this other term. And so we now want to sort of study the behavior of this, and also maybe translate this to the function case to see what this guarantee is about. So, so if you look at this in the okay, so I'll get to this. So if you recall what we did here, so we want to use these metric entropy ideas. So instead of directly, just to remind you, we can directly control this Gaussian complexity. We did this, for example, for this sparse regression case. There is there's another way via the metric entropy idea. So this complexity of Gaussian complexity of, let's say, a net can be controlled by the Dudley's integral, and so we did some sort of calculations. That's the lemma that we want to use. So instead of solving that critical inequality, it's enough to solve this version. This is some sort of an upper bound on that Gaussian complexity, and we sort of manipulated it a little bit. So if you recall, we can go back to the discussion that we had there. we want to apply this because for many function classes, the entropy estimates are known. So we'd like to use this to basically find delta. I just have to figure out, this is the L2 covering number of this set. So what is this set and what is the L2 covering number? So that's what we want to do. So if you go back to the setting that we have here, we're going to work with these two sort of semi-norms on the class of functions. One is the uniform norm, also known as soup norm, or infinity norm if you want. This is the maximum absolute value, basically. And then we also look at the this norm, which is the L2 norm of this vector. So given what phi was, this would be, what would this be, if you recall? So phi is 1 over root n. So I would, can you say it loudly?
1 over n.
1 over n summation I from 1 to n f of xi squared. Okay. This I'm talking about this one, right? Because it's just the L2 norm of this vector, the square, right? That's what it is. So this is sometimes referred to as the empirical L2 norm for the function. And so you'll see, so this is often written as Fn squared. Here in these notes, I'm writing it to avoid confusion like this, to avoid confusing with the case of n equal to 2. But this is the common notation. Why this is interesting is because if, for example, if xi's are, we're assuming things, xi's are deterministic, okay? So it's a fixed design setting, but if they're IID from some measure mu, then for any function, reasonable function, let's say L2 integrable, this quantity converges to what? If I draw xi's IID from some measure, this is an empirical average. Yeah, converges basically to the integral of, let's say, x squared d mu. This is written as the L2 norm squared. This is the population or the usual L2 norm with respect to that measure, and this is the empirical norm. So the empirical norm is an approximation of this L2 norm in the space of functions, and this is a very common norm to use. It's like the equivalent of the L2 norm for vectors. So that's why you care about this empirical norm. Again, the usual notation, for example, HDS or some other statistics book, they write it like that. To avoid confusion, I write it with a bracket here. So that's nothing but the L2 norm of this vector. Okay, it's just that we say that this is a semi-norm because it could be 0 for non-zero functions. It may not be. It just this guy does not necessarily imply that f is 0. If that's the case, then it's a proper norm. But for example, if f has value 0 at these points, but non-zero elsewhere, then it could be 0. But asymptotically, it approaches the L2 norm. The reason why we usually work with this is because if you don't make this assumption, this part is not, this convergence doesn't make much sense. But this empirical norm makes sense. So whatever we come, like come up with is going to be in terms of this. If xi's are from a random design, IID, then you can say this approximates the L2. That part is a little bit of a, it involves some hand waving, but hopefully this is justified. So this is the thing that we care about. This is upper bounded by this sup norm. Why is that? Okay, great. Yeah, so this is average of these values. So if I replace each one with the maximum value, the average is going to be less than the maximum. And then take the square root of both sides. So this is easy to see. Okay, so sup norm is an upper bound on this empirical norm. So we have, this is by definition basically, and this is less than f infinity. Okay, the sup norm is a proper norm. So if this is 0, and sup norm is 0, then f has to be 0 everywhere. Questions? Okay, so if you sort of look a little bit at this relation, if I compute the covering number of the class of functions f in this norm, the empirical norm, it's equivalent to looking at the covering number of phi f in the L2 norm in Rn. Okay, because of this relation, if I find two functions that are in the empirical norm less than or equal to epsilon, this is equivalent to saying that phi of f minus phi of g in L2 norm is less than epsilon, okay? And so basically I'm covering, this is, let's say, r theta, right? So I'm covering basically theta in the L2 norm if I'm covering f in the empirical norm, okay? And so that's one observation. The other observation is that this covering number in the empirical norm is going to be at most the covering number in the infinity norm or the sup norm. So why is that? Because of this upper bound, yeah. So if I have a covering in the sup norm, means that like f minus g in the sup norm are less than epsilon for like for every f there exists some g such that f minus g in sup norm is less than epsilon, then it means that f minus g in the empirical norm is also less than epsilon. So any covering in sup norm, epsilon covering would be automatically empirical norm covering. So whenever you have like dominance of norms, you can easily see that the covering numbers would satisfy this inequality. Okay. So the strategy is, so if you recall, in those entropy integrals, we had something like this. So we wanted to cover the theta in L2 norm. This is the empirical norm. The empirical norm is controlled by the sup norm. So if we can control the sup, like the sup norm covering number of f, then we have control of that covering number that appears in those integrals. So that's the thing that we want to do. So in order to introduce some more notation, the rest is sort of just notation. This is the essential idea. So if you write b sub n for the unit wall of the empirical norm, b sub infinity for the unit wall of the infinity norm, then if you recall, we had this theta, theta star sort of u or delta. This was basically theta. Okay, so that this was like theta. Let's worry about this version. I don't want to worry about this. So this is fs star n delta. This is nothing but f minus fs star. So we shift f to fs star, and then take intersection with the n. So basically, this is the set of all things that look like f minus fs star, where f is in f, and f minus fs star in the empirical norm is less than or equal to delta. So this is a neighborhood of radius delta in F centered at F star. So this is like the counterpart of what we had, like theta star. It was U or delta. So that was like basically, again, theta, if you go back, it's just basically B2, that was the L2 norm. So this is all the thetas that look like theta minus theta star, where theta isn't theta and theta minus theta star is less than delta. So basically the L2 covering number of this neighborhood in theta is exactly the same as the empirical norm covering number of this neighborhood in the function class. That's basically like perfect sort of correspondence. This is basically phi of this. So if you apply phi to this set, you get this. And if you recall, we're exactly controlling something like that. So in the L2 norm of this neighborhood, I'm just going to replace this with, so what we showed is that this is exactly the empirical norm. Just, it was an observation. Notation is like horrible, but it's just the neighborhood in F centered at F star of radius delta in the empirical norm. That's sort of all the indices that I could sort of put there. The idea is simple. So you have like F, there's a F star, and then you put a ball of radius delta in the empirical norm. So this is exactly that. So if you, I'm not going to go through the argument for this. The argument was sort of, we did this. The only piece that was missing was the Debris integral, the proof of the Debris integral, but that's sort of something separate from this discussion. So if you just replace that quantity there, you get this result, okay? And then we furthermore, instead of doing this, what we're going to do is we're going to replace this basically later on, because this is upper bounded by n infinity. If I can control the infinity norm covering number, then I'm done. Okay, so that's what we usually do. We'll see an example. So that's sort of our argument basically. So if delta satisfies this, then that critical inequality holds. If you go back to the critical inequality, that's basically this guy we have now defined to be sigma tilde. So if you go back in terms of theta, what you show is something like this. Okay, that's something that we show. In terms of the expectation, basically, we showed that 1 over n theta hat minus theta star squared is up to constant bounded by delta, let's say n. This is the smallest delta that satisfies this critical inequality, let's say. So delta n, the smallest solutions of this, smallest solution of this. So this gives me sigma squared over n, basically. Okay, so what is this guy? This guy in our case is 1 over n phi of f hat minus phi of f star. So you translate back, which is, sorry, not phi. Let's see. Yeah, there's no, there's an extra n missing here. So let's hope it works out. So this is actually itself is equal to, yeah, so this itself, well, from this you'd get theta hat minus theta star squared from this inequality up to would be like delta n squared plus sigma tilde squared, which is just delta n squared plus sigma squared over n. And this is like phi of f hat minus phi of f star by definition, which is nothing but the empirical norm. So the kind of result that you would show is that f minus f star in this empirical norm is up to constants bounded by delta n squared plus sigma squared. That's the final sort of bound. Okay. So bound on theta hat is like this, theta star is like that. And so you get a result like this. Okay. So yeah, once the dust settles, if you basically if you can solve this equation, find the smallest delta that satisfies this, that delta basically directly controls the expected empirical norm square. So that's this result. And what I would like to show is an example. Maybe I show you an example and it will become clear. So if, for example, if you have, maybe any questions, roughly. So the thing is that you have to track, but all these results are there. So if you go back, we basically translate them into the functional domain. The only thing that to figure out is the correspondence between the entropy, metric entropy numbers. So we're going to bound this by infinity, and like the infinity covering number. So instead of, usually you also even drop the delta. So this is saying I have to control the delta neighborhood, but you can just drop the delta, just the entropy number of the entire class is good enough. So this has a lot of bells and whistles attached. So a lot of this you can disregard in practice, like in some cases. It still gives you a good result. It's like almost optimal. So that's what we're going to do here. So suppose f is Lipschitz class with Lipschitz constant L. So this is the set of all f from x to r such that fx minus fy is less than or equal to L times x minus y. We're assuming that there is some sort of a metric structure. Let's say x is a subset of Rd. I think I'm actually assuming that x is a subset of Rn. So let's say we are doing something like this. Okay. This is the class of Lipschitz functions. Okay, so if what I want to do is like I'm assuming that yi is f star xi plus wi, and f star belongs to this class. So I just know that I have a Lipschitz with Lipschitz constant L non-parametric function. I don't know anything else besides this. This is really truly a non-parametric assumption. And then f hat is defined as argmin over f in this class. So you find the best Lipschitz approximation basically to these numbers, y minus f, etc. How you can do it is a different story, but so you have something like that. You solve this. The question is that, is this going to get close to this? How fast can I approach this? So from our discussion of the metric entropy numbers, we know that this Lipschitz class in R1, the metric entropy is L over epsilon up to constants. Yes?
What does that mean?
Yeah, okay, good. Anyone remembers what this means? It is, yeah, it's related. What I'm using it usually is, it writes, for example, f less than or equal to g. What does this mean? Right, there is some constant such that f is less than or equal to cg. And then g less than or equal to f means there is another constant, c prime perhaps, G is less than or equal to CF.
So this is the implementation of each of them, or
Yeah, so this is equivalent to, at least that's what I'm using this for. Okay, so there are constants such that this is less than or equal to this, and this is less than. Yeah, some people use it for asymptotics, but this is like sort of non-asymptotic version. So this is O of that. That's sometimes you can say this is F is O of G. G is O of F. I don't use the O notation because this is cleaner. And usually with these notations, you usually mean the constant is like a universal constant of it. So they're universal. Universal means like numerical. It's not attached to any other thing. Here, it could be a constant that depends on some other things that are constant in the problem. But usually when you write this, not always, but usually means that this constant just is like 2.5 or something like that. There's nothing else that depends on it. So that's what I mean here. So there's like constants like 4, 5, I don't know, 125. Like you can write it as like C1 L over epsilon less than C2 L over epsilon. Right? That's what it is. So up to constants look like this. That's what we discussed briefly. At least the lower bound I argued. The upper bound, it could be a homework problem, but probably not. But if you're interested, try to show this. It's an exercise in the HTTP book. So what we're going to do is, as I mentioned, oftentimes you drop this to 0. This gives you an upper bound. So as long as you have an upper bound on this, you can plug it in here and solve that. That would give you the delta that you get can be used here. So the smallest delta that satisfies this would be basically the lower bound on if you increase it, you can see that basically any delta that satisfies this works. And if you have an upper bound, once you satisfy this inequality with an upper bound on this, you also satisfy this inequality. So we're gonna like work out with an upper bound. So drop this to 0, I get an upper bound. Also drop this delta. So what I'm gonna control is basically integral 0 to delta of root log n infinity epsilon f star, dropping the delta. Okay, so it gets bigger, d epsilon, and this is bounded by like a constant here, sigma squared root n over sigma, something like that. Delta root n over sigma. I want to solve this. And I also note that f star belongs to f Lipschitz 2L, right? Because this is the class of all functions that look like this, where f belongs to f Lipschitz L. Right, so if I take 2 Lipschitz functions and subtract them, the difference would be at most 2 Lipschitz, 2L Lipschitz. It's easy to show. So instead of doing this, I'm going to solve basically, and I'm going to just disregard this constant. You would see I would write something like, I'm going to solve this inequality, log n infinity f Lipschitz 2L. This is an upper bound. Whenever you put an upper bound, it's going to work. And I'm going to put this up to constants. I want it to be delta root n over sigma. Okay. Now I have an upper bound on this side. So I know that this is, again, up to constants is L, V2L over epsilon, but it's up to constants L over epsilon. You can see once you don't worry about constants, things would become simpler. So that's our bound. So what we would do is we plug this in here, right? So you'd get that this integral is upper bounded up to constant by 0 to L to delta root L epsilon d epsilon. So I get root L epsilon to the minus 1/2 d epsilon. So what is this integral? What is right, root epsilon. Is that correct? Okay, so then there's like also root L here, and then I have to do from 0 to delta, right? So you get 2 root L epsilon, right? No? Delta, yes, delta. Right. So in the end, I can say up to constant, this is just root L delta. Okay, I have an upper bound up to constant. I'm going to set this upper bound less than that. I want this to hold. So this is satisfied if so anything that implies this is good enough. Just verify this for yourself, going through the argument. So as long as this is less than or equal to. So the whole point of these calculations is that it gives you a simple way of actually figuring out what the rate of convergence is. So the delta that satisfies this, the best delta, the smallest delta that satisfies this controls the performance. So how do we solve this? We can simplify. So this is like root delta, right? And I'm going to put sigma here, root n here, right? And then I can square it. This is equivalent to sigma squared L divided by n. Okay, so the delta has to be bigger than this, so the smallest is like up to constant equal to this. So that critical radius delta n is, you can say it's at most this because it's the smallest, so it can be this, has to be, you can say something like that. That's the critical radius. Okay, sigma squared L over n. I'm going to plug it into, did I make a mistake here? I made a mistake somewhere. Oh, there's a square here. You missed the square. There should be a square. This was too good. Yeah, there's a square here. So what would happen? If I simplify, this would be what? 2 minus 3 over 2, right? Is that? No. 2 minus 1/2. One of these would go away with that. And 2. Is this correct? So this is like that. Then I square both sides. I get rid of the 1/2 here and this, and then 1/3. So I get that. So this should be 1/3. Okay. And then the rate would be delta n squared plus sigma squared over 2, because delta is of this size. That's what exactly we have here. So the rate would be delta n squared plus sigma squared over n, which is at most sigma 2L over n. 2/3 plus sigma squared over n. This is dominant because 2/3 goes much slower. Let's say L is bigger than 1. Then this is going to be dominated up to constants by this. This is the parametric rate. This is a non-parametric rate. So at the end of the day, you get this rate. which is actually optimal for this class. So you can't do better than this if you're doing uniformly over all Lipschitz functions. But this shows the difficulty of non-parametric estimation. Okay, so if you just want to be general, don't want to assume anything besides being Lipschitz, then your rate is not going to go down. So if it was parametric, it would be sigma squared over n. Now it's sigma squared, ignore the L, let's say L is 1, sigma squared over 2 to the third, 2 over 3, which is slower, much slower in practice. So you can do some sort of calculations for yourself. What happens, like, in order for me to like half, drop this by half, how, like, what like number I should multiply n by, and you can see it's much larger for this, so you need much more samples. And you can also see sigma squared over n appears here. This is very natural. So sigma squared over n is the like basically noise per sample in our problem. So individually sigma squared or n do not matter, but the ratio sigma squared over n matters. The same goes for usual regression. So it was a little bit tricky, but all the things that we discussed, things were sort of simple. You put them together and it allows you to prove a result which is non-trivial. This is very non-trivial.
Why which is constant it's not large? How's larger?
Usually you'd assume, I mean, usually you don't care about this. Well, if it's constant, you can just absorb it into this. What I'm doing here is just, I want to upper bound this by, I want to say that this is bounded by L sigma squared over n. If L is bigger than 1, this is going to be true. The way I wrote it, L could also vary with n. But just if you think of L as fixed, you can just drop it from everywhere, just absorb it into these constants. It is bigger. Sorry? Yes. Yes, and the rates are increases, like the gets worse. If the class is larger, the rate should get worse intuitively. Right? If I know, like, I want to decide between 2 functions, this is an easier problem, like deciding between 3 functions, right? Yeah, the main issue, like the main point is that this is not a finite dimensional class. So if you're basically approximating a function which is Lipschitz by endpoints, and also do it under noise. This is not it's not an easy problem. Okay, and if L is bigger, this is a bigger function class. You would have basically you can argue for yourself that there's a trade-off. For example, I can always find this problem. If I know L, I can always divide everything by L. So you get sigma over L, and I can assume that this to be like 1 Lipschitz. Oh, you're saying, okay. Yeah, it's a little bit tricky. So I think I understand what you're saying if L is bigger, then this is a bigger function probably as it's noise. It should be easier. But the function class is also bigger. That's the, I see your point. Okay. So you'd like to say that if L is bigger, this L has to appear something like sigma squared over L squared n, something like that. Yeah, the issue is, yeah, I never thought about this, which is very interesting. the entropy number is going to be bigger. That's for sure. So if I know L, I can always, yeah.
That is because probably because our function class becomes larger, it's more hard for us to get this.
Yes, that's what I originally thought. But you can do this argument. So if I know L, I can divide everything by L here, right? So I get yi divided by L. F star divided by L would be 1 Lipschitz. Now my noise is sigma over L. So I can apply exactly the same result to these new observations. And, oh, okay, I get, yeah, this works. So you get like F over L. Would they cancel out?
If you have that over squared, that cancels out. If you multiply that over, you have sigma squared over.
All right, so let's try to do this. Yeah, one of the issues is that I'm assuming L to be bigger than 1 here. So if you have yi is equal to f star xi plus sigma squared over, sorry, sigma squared wi, f star is L Lipschitz. So I can define y, let's say this tilde is different, to be yi divided by L, right? And f star tilde to be f star divided by L. And sigma squared tilde would be sigma squared divided by L. So I get yi is equal to f star tilde xi plus sigma 2 tilde wi. And now f star tilde is in class 1 Lipschitz. So if I apply this result, I get f hat, let's say tilde, minus f star tilde. This is going to be sigma squared over n to the sigma squared tilde over n to the 2/3, okay? Now if this would be like f hat xi divided by L, where f hat is the original one. This is f star divided by L, if I'm not wrong. So this is sigma squared over L squared n. So what do we get? Multiplied by L squared, I get, what do I get? This is L squared, this is L squared to the 2/3, sigma squared third, so I get L squared to the 1/3, right? Is that right? So do I get L sigma squared? So it seems like we get back. Is this correct? So things are consistent. Okay, we didn't run into contradiction. So it's not gonna like work. So you can't sort of. It just intuitively I understand what you're saying. So if this seems like a signal, increasing signal to noise ratio, but this also increases the function class. It's not like the way to change the signal to noise ratio is to reduce sigma. Increasing L just makes things worse. It's an interesting sort of comment. Thanks. But do this hopefully like repeat this, hopefully, things should be scale invariant. So if you know L, so that the thing that I did, it's good to like do these checks. So for example, if you divide everything by sigma squared, you can assume sigma squared to be 1. In the end, the results shouldn't change. So this just tells you that this is the scale of the problem. So any questions? So now that you see that this is useful, I just want to go back and prove the result that we started with, which I didn't prove. So all of this is based on this very simple result. Not very simple, but it just starts from this. And then you can see, like, we manipulated this. This critical inequality, once you define, this simplifies to this bound basically tells you that this delta is controlling this. But we didn't prove this. So how to prove this? Just want to do this here. How do we prove this? The proof is basically, let's say there are two lemmas. Lemma 1, which can be assigned as problems for you to do. If this is like this, then for all t and u bigger than 0, with probability greater than or equal to 1 minus e to the negative t squared over 2, supremum theta in this theta u, w theta is less than gamma theta u plus tu. So this quantity here is just expectation of the left-hand side. If you remember, this is the Gaussian complexity. So this is nothing but the expectation of the other side. Okay, this is one lemma. So think about why this lemma is true. Tell me why this is true. The next lemma is, say, lemma 1. And then we have lemma 2, which is saying that assume theta is star-shaped. And then let fu be, this is a deterministic lemma, theta and theta u. Then w theta less than or equal to max theta 2 over u. All theta in theta. That's the next lemma. So theta u is just theta intersect with u times b2. It's just the set of all thetas in theta such that norm theta 2 is less than u. It's a neighborhood of size. So the second one is a little bit strange, but this is a very nice way of, so this is saying if I control the supremum of this function over a ball of radius u in theta, then I get to control it for all theta via this inequality. The star-shaped idea tells me that if I can control it over like a neighborhood, then I can control it everywhere to some like extent. It's not just that's what it is. So why the first one is true? Any idea how to? It's better than a sub-Gaussian bound. Yeah. So this is what it's saying is that this guy, the supremum, is sub-Gaussian essentially, like one side of the sub-Gaussian. But why that supremum is sub-Gaussian? So W is Gaussian, is a Gaussian standard Gaussian vector. So what do we know about? Yeah, so this is a linear combination. So this is sub-Gaussian. This is actually Gaussian. But this is not like this function as a whole is a complicated function of W because there's a supremum involved. So this is a general function of W. What do you know about concentrations of? Sorry? Yes, so you know that Lipschitz functions of this would be concentrated. So the strategy is to show that this is a U Lipschitz function. And it is indeed. So proof, you can do as an exercise proof. This guy is a U Lipschitz function of W. The fact that this is restricted to a ball of radius U makes it a U Lipschitz. Just prove it for yourself. You take W and W prime, call this f of W. And you look at f of W prime, you want to show that the difference is like bounded by U times the norm of W minus W prime. If you have this, then this follows from concentration of Lipschitz functions of the Gaussians. That's one of the most powerful results that there is in concentration. Okay, that's for you to verify. Lemma 2, how should we show the lemma 2? So if theta is, if theta is in theta and norm theta is less than U, right? It's already in this. So we know that this guy is bounded by FU by definition. So that gives me this part. So FU, so this is either upper bounded by this, which is this case. But what if theta is in here and norm theta is bigger than U? How should I control this? Great, that's exactly what we're going to do. So theta divided by norm theta times U, that's sort of, this is theta here. I'm going to scale it down until I hit yeah, what we're doing here is just, let's say you're inside the set. This is my set, right? Theta is outside. This is ball of radius U. Theta is in. This is capital theta. Theta is in there, but outside the ball. What I'm going to do is I'm going to drop it to this point. That's what is going to do it. So on the same basically ray extending from 0 to theta, I'm going to drop it. That's what is going to do it. This point is guaranteed to stay in theta. Why? Because, yeah, so this is going to belong to theta, since theta is a star shaped. Now I can apply the result. So I know that norm W theta then, so case 1, case 2. Then I know that W and theta over U, this times U is going to be less than F of U, right? Because now this is inside theta and also inside, this is going to be in theta intersect with UB2. So this is in fact inside theta U. Right, so now I can apply this. And if you just rearrange, this is just saying W theta is less than or equal to theta divided by U. If U. Okay, this gives you this part of the line. It's either bounded by FU or bounded by this. So you can just uniformly control it everywhere. Okay, that's the nice thing about the star-shaped business. That's like case 2. Okay, now how do we prove? Just the result just follows easily from this too. So first, it's a proof of the theorem. So recall that we had yi is equal to theta star I plus sigma wi, I from 1 to n, or in other words, y is equal to theta star plus sigma w. I had theta hat, which is argmin theta minus, or y minus theta squared, theta in capital theta. So what we have here is a general idea is to write a basic inequality. So basic inequality. So we say y minus theta hat norm is less than or equal to y minus theta star. So why is that the case? Sorry? Yeah, so this is the argument. You're assuming that theta star belongs to, so theta star is feasible. So this is the assumption that we discussed. So assume that theta star is in there. And theta hat minimizes overall thetas that are in there. So theta star is feasible, theta hat is optimal. So this is sort of optimality condition. Next, we're going to just replace this with theta star plus sigma w. Right, you get theta star plus sigma w. This gives me that delta hat be theta hat minus theta star. So this gives me sigma w minus theta hat less than sigma w squared. Right. So I square this. One of the terms gets canceled out. So I get delta hat squared. The other term, I'm going to move to the other side. Sigma w delta, the other term cancels out. So this is the basic inequality. Okay, I'm going to put 1/2 here. That's something that we get after simplification. Okay. Next, what is next? I want to use these two lemmas. So if you look at this, so delta hat belongs to theta star, right? This is the set of all theta minus theta star where theta is in capital theta, right? So what I want to do is that, so this is star-shaped by assumption. After centering, it's star-shaped relative to 0. So I'm going to apply these two lemmas to this theta star, basically. So if I apply lemma 1, by lemma 1, I have that supremum theta in, I'm going to write it as delta in theta star u w. This is just a dummy variable, so I'm writing it for simplicity as this is less than gamma theta star u plus tu with probability, that probability that we had. So this is nothing but GUT, if you remember. That's what we defined. So that's, you can see where it comes from. There's the expectation and there's like the tail bound. So that's something that we have. So this is now a good place to apply lemma 2. So this is like f of u. So I have this supremum is controlled by this, okay, over this part, and this is star shaped. Because theta star is star shaped, this is also star shaped. What I get is that from this, I get that W this is going to be less than or equal to norm divided by U1 maximum of this. I'm going to write it like this. This is the notation for maximum. Okay, for simplicity. Max, this is another notation for it. Times f of u, which I can upper bound by this g ut. So this holds for any delta in theta star, not necessarily u. What I'm sort of doing is I'm removing this condition, right? That's what this lemma says. If you control it over a neighborhood, then it can just remove the neighborhood. That's the two piece. So this is lemma 2. So first control it over a neighborhood of your radius u. That's this with high probability 1 minus a to the negative t square root of 2. And now I have it for all delta in this. And this is a uniform result. This holds for any delta. And this random delta is in there. So usually you need a uniform result because if you have seen these arguments, this is dependent on W. It's not easy to control, but now I have a uniform result. This holds for any delta in this set, and I know that this definitely is in that set. So now I can apply this to, so uniform result applies to delta hat, which then gives me W delta hat is less than or equal to delta hat 2 over U. This is V GUT. Okay, that's the result. Now combined with the basic inequality, right? This was the basic inequality that we had above there. So sigma W delta hat. Combine them, what I would get is 1/2 delta hat 2 is less than or equal to this guy over U V1 and then sigma GUT. Okay, that's basically the end of the story, more or less. What I get now is I can simplify. Either this is the bigger one or this is the bigger one. Okay, if delta hat 2 over U is less than or equal to 1, then this gives me 1/2 less than or equal to sigma GUT, which gives me that delta hat is less than 2 sigma GUT, the square root. Okay, or this guy is bigger than 1, then I get 1/2 delta hat 2 less than or equal to delta hat 2 over U sigma GUT. Right, this is the second case. I can now do this. Right, what I get is that delta hat 2 is less than 2 sigma GUT over U. So I'm either less than this or this. So the two cases I can summarize as conclude in either case that this is less than the maximum. 2 sigma GUT over U and root 2 sigma GUT. That's basically the result that we had there. Okay. So it's a clean argument. It's not non-trivial, but like every step is very simple. The main sort of case is like using the Gaussian concentration to relate this supremum to in a neighborhood to the expectation. That's the Gaussian complexity, and then use the star shapedness to say that once I control over a neighborhood, I have a control over the entire set, and apply this to theta centered. The deviation lies in that set, and then you write the basic inequality and just simplify. This is very similar to if you go back to our analysis of constraint lasso, there, for example, delta hat was in some sort of a cone, right? And over that cone, we had good control. Here, this is in the star shape. You need to do some sort of argument. Very similar argument would work if you have regularization, for example, by a norm. Then it would look like the lasso type argument. You have to like force this. So this is in this set, if you have regularization, there's no guarantee that this is necessarily in the set of interest, but you can force it to be in the set of interest and so on. But just go through this argument for yourself. If you have questions, let me know. This is the basic one, then the rest, everything is proved. So if you go back, we have proved everything. Except this, now you have this, so everything follows. So you have a complete proof that if you do non-parametric regression on the class of Lipschitz functions, then you get this weird non-parametric ray. Okay.